Okay, so if you think back to your linear algebra class, there was something that we called the characteristic equation. Now, in this class, you've heard me refer to this as the auxiliary equation, if you remember from chapter 4. And I want to start to show you other ways that you can solve systems of differential equations. Okay, so let me start with, so what is it that you want to solve? Well, this, remember, what I have boxed in right here, this is some system of differential equations. Of course, we're in first order right now. This is some system. So this is the thing you want to solve. Now, the solutions to these systems are going to take the following form. Now that you should have seen this before, or recall seeing this before. This should look very similar, only we had r values here instead of this lambda. So this is the form that the solutions are gonna take. Only that now you're used to seeing it as c sub 1 e to the r, say sub 1 t, plus c sub 2 e to the r sub 2 t. You're used to seeing the solutions in that form. This is the same thing if you were to distribute each scalar. Now I want to take a second and discuss each of these little parts here, because I don't. So let's discuss, what does c sub 1 represent? So this is, c sub 1 is some constant of x sub 1. C sub 2 is some constant of x sub 2. All right, and then of course this lambda dA. So this lambda is also another scalar. So notice that you have all three of these are just scalars. So c sub 1, c sub 2, and lambda are all scalars. All right. Now, what we're going to do to make things easier is we're going to let C, just capital C, represent that vector c sub 1, c sub 2. In other words, now you're going to see me, I'm going to rewrite this, but instead of having this vector c sub 1, c sub 2, I'm just going to have a capital C. So the same thing. All right, now how do I show that this is a solution? So I'm going to go ahead and, forgive me, my papers fell. I'm going to go ahead and do some quick substituting here. So on the next page, you're gonna see me substitute, because remember, this is what you're trying to solve, right? And this will give you a hint of how we're going to do this. So we're going to substitute in for x here. We're going to substitute in for x prime here. And I'm going to do that right now. So at this stage, I've substituted in for x and x prime. And now this is not something to gloss over. This is something that is going to help you see how we go about solving these in using matrices and so forth. So in this case, let's take a look at what we have here. Now, what I'm going to do is I'm going to write this off to the side, but I'm going to divide both sides of this equation by e to the lambda t. Now I can do that because I know that e to the lambda is just a scalar, so e to the scalar t will never equal 0, right? You can't even if lambda t equals 0, e to the lambda t would still equal 1. So I'm gonna divide by e to the lambda t. And now let me rewrite what we have at that point. So now we just have c lambda is equal to a c. Okay, and again, just keep in mind that c is equal to c sub 1, c sub 2 as a vector. Okay, now, again, how do we get to solutions? Well, at this stage, let's set equal to 0. All right, so now I would have 0 is equal to ac minus c lambda. All right, now, at this stage, I'm gonna factor out a c. Almost there. So I end up with 0 is equal to c multiplied by a minus lambda. And now, had this been in a classroom, and I could look at you and in real time ask you a question, I would call out any of my students who are in linear algebra right now. Tell me where you've seen this before. And assuming that you could still answer this question if you've looked at chapter 5 videos in linear algebra, but you would tell me, oh, wait a minute, that is that characteristic equation. I remember seeing that before. Now, the only thing is I need to adjust this, right? Because structurally this makes no sense. We have A as a matrix and lambda as a scalar, right? It makes no sense if you have some 2 by 2 matrix minus some scalar like 5, right? Like that structurally makes absolutely no sense, because you can only add or subtract matrices from matrices. So I need to be able to write lambda. I need to be able to write lambda as a matrix, but I don't want to change it. I need it to still be lambda. I just need to write it as a matrix. So, and to do this is very simple. Remember, anything lambda multiplied by 1 is lambda. So all I'm going to do is I'm going to make use of that identity matrix, so that, and I'll go ahead and write it, so that I can write that scalar lambda as lambda 0, 0, lambda, right? So this is just the matrix analog of the scalar that is lambda. So I'm going to go ahead and do that now. So we're just going to multiply this by the identity matrix I. And at this point, let's make sure we understand what we want. Okay, so clearly if I choose a scalar of 0, right, that would mean you have 0, 0 as c sub 1 and c sub 2. Clearly that would work. But that's not what I'm interested in. I'm interested, so let's go ahead and write that. So clearly if c equals 0, right? In other words, c sub 1 and c sub 2 equals 0, then you would have the trivial solution. We're not interested in trivial solutions. So, therefore, what we care about is when a minus lambda I is equal to 0. Right? Because I don't care if I just choose c is equal to 0, then that's just a trivial solution. So what I care about is when a minus lambda I is equal to 0. Now, the next thing I need you to understand is that this is a matrix minus a matrix, right? So a minus lambda I is a matrix. So now see if you can follow me down here. So since a minus lambda I is a matrix, And what we want to do is we want to try, we don't want that to equal 0, right? We want to try, we don't want this to equal 0 because then we just have the 0 matrix. So what we really want is we want to try to figure out when does A minus lambda I not equal 0. Well, what is a way of figuring out, helping us figure out when something equals 0 or something does not equal 0? Well, it's that determinant. Now, if again you would have seen this, you could have brushed up on this using that crash course in matrices video, or you can look back up how to take determinants in your notes from previous classes. But the idea is the determinant of that matrix is what's going to help us here. Finally, all I'll do is I'm just going to, just like in linear algebra, that lambda is what we call eigenvalues. Okay, so we have what we need to proceed with solutions. All right, so here's the way here's the very first question where we're gonna start to use this characteristic equation to solve a system. All right, now I went ahead and I used y's and y primes instead of x sub 1's and x sub 2's for this first problem. And you tell me if you don't like this method better than the methods that we used in chapter 4. Of course, this is with a very baby problem, but let's go ahead and proceed. So what do we want to do? We want to solve a system using eigenvalues and eigenvectors. All right, well, what is the system that we want to solve? Well, that is the following system. We want to solve the following system. Now, they give us a little bit more information. So clearly, we already know that the normal form is x prime is equal to ax. But they go ahead and tell us that A is a 2 by 2 matrix, and they tell us what it is. And furthermore, they didn't have to give us this information, but lambda I would be written as a 2 by 2 matrix form. So how do we proceed? Well, we proceed by starting with the characteristic equation. So this determinant of A minus lambda I is where we begin. And this is the characteristic equation. All right, so what I'm going to do is I'm going to go ahead and fill in some information. I'm going to plug in what I know about A. I'm going to plug in what I know about lambda I. So let's do that. So now we would have the determinant of 4, 2, negative 1, 1 minus, in this case, it's lambda, 0, 0, lambda. And we know that that's equal to 0. Okay. So first thing, let's go ahead and subtract. Let's go ahead and take care of the subtraction first. So that's going to be the determinant and we would have 4 minus lambda, then negative 1 minus 0, then 2 minus 0, and then 1 minus lambda. Okay, so at this stage, if you want to solve the system using eigenvalues and eigenvectors, it's at this stage right here where you're actually going to take the determinant. Okay, and remember that the determinant, this is again, this is in a previous video, is going to be, so the determinant of A, B, C, D is A, D minus B, C. So we're going to do that right now. Ready? So let's go ahead and take the determinant. So that's going to be 4 minus lambda times 1 minus lambda minus negative 1 times, we've got 2. And that's still equal to 0. All right, let's go ahead and FOIL that out and combine like terms. So we end up with lambda squared minus 5 lambda plus 6 equals 0. All right. Now, doesn't that look similar to the y double prime minus, y prime plus y, where we had our a's and b's and c's here, right? Remember that? And you would go from there to auxiliary form. Ah, very nice. So you didn't know at the time that you were actually finding eigenvalues. So this this is nice, and this actually factors to lambda minus 2 times lambda minus 3 is equal to 0. And finally, let's make a statement. So in this case, lambda is equal to 2 and 3. All right. So what are these? These are your eigenvalues. All right. So we're going to use, and I'm going to need some more space here. Let me grab this page, bring it up. So let's use those eigenvalues to find the eigenvectors. So we had eigenvalue just like r sub 1 and r sub 2, but ours is lambda sub 1 is equal to 2, and lambda sub 2 is equal to 3. Let me confirm. So 2 and 3, right. So lambda sub 1, lambda sub 2, just like r sub 1, r sub 2, right. So now let's find, now we're going to find the eigenvectors. Right, so you should say the eigenvectors associated with the eigenvalues. It would be the proper way of stating it. So, okay, let's start with the eigenvalue of 2. All right, so now we're going to find the eigenvector. So let's go back to that a minus lambda I, but we're not using the determinant this time because we're actually trying to figure out what the eigenvector associated with that eigenvalue is. So, okay, so what's going to happen right now is we're going to plug 2 in for lambda, and we're going to go ahead and rewrite c back as c sub 1, c sub 2. Okay, that's how we shorten the process just so things don't get cluttered, but let's get back to the proper form. So that would be a minus 2i, and then let's go ahead and write c sub 1, c sub 2 is equal to 0. Okay. So do we know what a is in this problem? Well, we do. A, we were told, was 4, -1, 2, 1. So what we're going to do right now is we're going to plug this in for a, and we're going to write 2i as a matrix. Okay? So 4, -1, 2, 1, minus 2, and if you don't mind, I'm going to go ahead and write that. You know that it's an identity matrix, 1, 0, 0, 1. So I'm going to go ahead and write that as 2, 0, 0, 2. And then still, here's our scalar, c sub 1, c sub 2. All right, well, a little bit of arithmetic brings us to the following matrix. 2, -1, 2, -1, c sub 1, c sub 2 equals 0. All right, so how are we doing so far? All right, let me, I remember I dropped my papers, so now I have to play the game of figuring out where my papers went. So entertain yourself for just a quick second. Did I do actually? Yeah, everything's. I think everything's perfect. What is not perfect is where all my papers went after I dropped them. That is the part that's not perfect. All right. Well, I could continue here, but I think I can just finish it without looking back through my notes. But let me see if I can. Let's see if I can. No, I can't. I can't. Let me just make sure I don't make any silly mistakes. So, all right, I'm gonna pause the video. When I pick back up, I'll finish this guy.